Welcome students. Welcome to my third video of Everyone Can Do Calculus. Today on this video, I will talk about the squeeze theorem, which is a little bit fun, right? So today's lesson objectives are pretty simple. After watching this video, I want you to do, I expect you guys to know how to evaluate the limit using the squeeze theorem. And this is very important. But before we actually start with the squeeze theorem, let's kind of go over what we learned in last lecture, because those are pretty relevant to what we're going to do today, okay? So on the last lecture video on evaluating the limit, what we did was we used a direct substitution property to evaluate the limit. And then this was very good. The direct substitution property was very important because using this property, we could skip all the limit laws. We actually discovered that using the limit laws when we're evaluating limits are very tedious. It takes a lot of time, and then we don't want to, and then we really want to skip that. That's why we are using a direct substitution property to skip those steps, right? And then other than the direct substitution property, we learn how to evaluate limits using graph, tables, and algebra, right? Those things are very important. So first one, DSP, which is a direct substitution property. So what the direct substitution property said, if the function is polynomial or rational function, right? If the function is polynomial or rational functions, then, and this is very important, and then A is in the domain of F. So which means that where the x is approaching to, the a value has to be in the domain of the f. Okay? So then the limit value, the limit of fx will be exactly be equals to fa. What does that mean is that you don't have to evaluate it through the limit law, but instead of using the limit law, you can just plugging in that value to the function. So just plugging in, right? Not using a limit law, we're plugging in the value. So that's the key of the direct substitution property. So for example, let's kind of look at our first examples right here. So it said x is approaching to 2, and then the function is x to the fourth power minus x to the third power, and this is polynomial, right? This is polynomial. Therefore, the domain is all real number, which means that every number can fall into this domain, which is the 2 is in the domain, which means that we can use this direct substitution property. So without using a limit law, we're just plugging in. So limit value x2 of x to the fourth minus x to the third is equals to just 2 to the fourth power minus 2 to the third power. And then 2 times 2 times 2 times 2 is 16 minus 8 will be equals to 8, right? Very easy. We can skip all the limit law. And same thing for the rational function, right? This rational function, the domain is very simple, which is x cannot be -3 or 2, right? But our x is approaching to 3, which is a 3 is in the domain of these rational functions, right? So since the function is rational function, and second, the 3 is in the domain of the function, we can use a direct substitution property. So we're just plugging in that value, right? Which means that the limit of x going to 3 of 1 over x plus 3 times x minus 2 will be equals to, we're just plugging in the value, which means that we're going to get 6 times 1, which will be equals to 1 over 6. Right? Pretty simple. This was pretty simple. But it was not simple in the case that what? In the case that when the A is not in the domain. For example, if you actually look at this function, right? The domain of this function, this is rational function, by the way, but the domain of function is that x cannot be equals to 4. But however, if you actually look at the limit, our x is going to 4, right? Our x is going to 4, while the domain said x cannot be equals to 4. So that's why we cannot use a direct substitution property. So what are we going to do? What we are going to do is that we are going to use algebra so that we can figure out the way that we can get rid of this denominator so that this 4 can be included inside the domain of the new function. So our goal is that we want to delete that part, because without that part, the 4 will be definitely can be inside the domain of the function. And then we can use a DSP, right? But right now, we cannot use a DSP. So here, what we're going to do is that we're going to use algebra and try to delete the denominator. And then I told you that every time when we see the radical, the one way that you can think about it, like a 2 minus radical or radical plus like number, like some kind of, those kind of number are always a conjugate problem. So this problem has to be solved using a conjugate. So which means that limit x minus 4, x to the 4 of 4 minus x and 2 minus radical x, we're going to multiply 2 plus x on the both of the side, right? And then what we are going to get is that we're going to get limit x is going to the 4. And then because make sure that you remember that conjugate a plus b times a minus b is equals to a squared minus a b squared, right? So on the denominator, 2 times 2 is 4 minus radical x times radical x is equals to x, right? So it should be 4 minus x, right? On the bottom. And in numerator, we are not foiling anything. Why? Because we can see the clear cancellations with 4 minus x. So this one has to be canceled. And then the answer has to be, right? And this one has to be limit x is approaching to the 4 of 2 plus radical x, which means that it should be equals to 4, right? Because here, right here, we can use a DSP, right? Why is that? Because 2 plus radical x, 4 is inside the domain of 2 plus radical x, right? Then we can use a DSP, right? So there we can use a DSP. Right here, let's kind of look at the next example. In this problem, it's pretty confusing, but negative 2 is definitely not in the domain, right? The domain is x cannot be equals to negative 2 for this part, right? Because if you put a negative 2 to the third power, negative 2 to the third power is negative 8. The negative 8 plus 8 will going to make 0, and the denominator cannot be equals to 0, right? So this cases, we need to do something with the denominator so that the negative 2 can be go inside the domain of the function, right? Then we can use a DSP. So in this cases, what we are going to do is that we're going to factor out the x third plus 8. Make sure that you memorize the cube factoring, okay? Difference and sum of the cube factoring, which is that a cubed plus ab cubed has to be equals to what? A plus b and a squared minus ab plus b squared, right? This has to be our factoring, right? So for this case, let's kind of factor this out. So limit x is going to the negative 2, and then we are going to factor out using the factoring rule, which is that what? X plus 2 and x squared and minus 2x plus a 4, right? And then the numerator will still be x plus 2. What we're going to do is that we're going to cancel that out, which means that now, because the x plus 2 is gone, x is equals negative 2 can be go inside of this function, right? Now the x equals negative 2 became a domain of this function, right? Part of this domain. So what we're going to do is that we're going to use a DSP and we're going to directly plug that in. So we're going to plug that in, which means that the answer will be equals to 1 over negative 2 squared minus 2 times negative 2 plus 4, which means that you're going to give me 4 plus 4 plus 4, which is 1 over 12. Right? So this was pretty simple problem, right? And then the next thing that we learned was the how to do it with the graph, right? So this function, this graph is pretty easy to graph, right? Because if you actually try to graph this, at x equals 2, the function has to be quadratic, right? The function has to be quadratic, therefore with 2, you're going to be landed 3, and you know that it will going to be make the quadratic because this function is quadratic function and vertical shift by 1. So it originally looks like this, right? It originally something looks like this, right? And then it is included, therefore it should be closed circle, right? And then when x is less than 2, your function has to be what? Your function has to be x plus 2, right? It should be x plus 2. So you can observe that when x is equals 2, it should be 4 and open circle, and then it should be crossing this 2. So the graph has to be looks like this. So the graph looks like this. So without actually doing any algebra, with the graphing, we can definitely know that the left limit and right limit are not equal to each other, right? Our left limit and our right limit are not equal to each other, right? At x equals 2. Therefore, the limit x is approaching to 2 of fx does not exist, right? That should be the answer. Why? Because the left and right limits are not equal to each other. There's another way of doing this, like using algebra. We can definitely just compute it out, the left and right limit. So our left limit, if you think about it, we are approaching to 2, right? Because we are approaching to the 2, it should be coming from the left side. So it should be the left portion of the graph, right? So our left limit should be evaluated using this one, right? X plus 2. So which means that limit x is going to the 2, x is coming from the 2 to the left, has to be x plus 2. Our fx has to be x plus 2 because it's coming from the left, right? So the portion that we need is only this portion only, right? For our left limit. So, which means that this is actually work as a DSP. Why? Because x plus 2, 2 is in domain, right? So therefore, this has to be equals to 4. And using the same logic, our right limit, the limit coming from the right, what we only matter with computing this right limit is this part, right? This part only. So our fx will be equals to x squared plus 1, which is that it will be equals to. And then this should be equals to 5, right? You know what? I think I graphed this wrong. I think the graph has to be something like 5. Sorry for my mistake. I was pretty stupid, right? I'm so sorry, right? So we can definitely compute this left and right limit algebraically, and then we can conclude that the left and right limit does not equal to each other, therefore limit does not exist. We can actually do this, right? So let's kind of do this. Let's kind of next thing is that we can actually evaluate it using a table. By the way, here the answer must be DNE, right? Because I told you that this means that there's a vertical asymptote at x equals vertical asymptote at x equals 2. And then vertical asymptote always means that the limit is going to the infinity. And then infinite limit is always a DNE, right? So, which means that this limit has to be DNE. But however, the reason that we are using a table is sometimes when we are trying to graph it, sometimes we need to know if this is going to the positive infinity or sometimes it is going to the negative infinity, right? So which means that in order to know the where is it going, right? We can definitely use our table to see where the limit is going to, right? So limit x is, so we can actually use a table for the right limit, right? For the right limit, we can actually use the table x and 1 over x minus 2. And that's why from the right limit, you should approach it to the 2, right? And then as you see, if you plug in 3 to the x, we get 1. Let's say if you're getting 2.5, we are getting 2, right? And then if you plug in 0.1, we are getting what? We are getting 10. And then 2.01, we get a 100. 2.001, we are getting 1,000, something like that. So it means that as we approach this to number 2, you know that our y values are becoming higher, 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 higher. So if our value, as our x is approaching to the 2, our fx value will going to be increased forever, which means that it will be going to the infinity. So this limit is actually going to positive infinity. So something like that. You can definitely use a table to see where the graph is going, even though, but what you need to know for sure is that even though the limit is going to infinity, it's still a DNE. Why? Because infinity is not a number. Okay, infinity is not a number, so you cannot say that the limit exists there. So that's the 3 things that we learned. So let's kind of try to solve this question using what we learned before. So here, let's kind of try to solve using a graph, okay? Let's kind of try to solve using a graph. So this is, right now, as you see, this graph is a graph of x times sine 1 over x, right? But as you see that, it looks like the graph is converging. The graph is actually going to 0, right? According to the graph. But it is oscillating, right? It is oscillating crazy, right? Oscillating really a lot of time. But even though it is oscillating infinitely, it looks like it is going to the 0. But I told you in the first lesson that whenever the function is oscillating, there's a high chance that it is a DNE, right? For example, let's kind of look at sine 1 over x function like this. Like, as you see that the function value is what? Is oscillating from 1 and a -1. So, which means that because this is oscillating infinite time, right? This is oscillating infinitely, we cannot actually evaluate if this is the left and right limits are equals or not. The left limit can be -1. The left limit also can be 1, right? Right limit can be 1, or right limit also can be -1. We cannot define our left limit, right limit, therefore limit does not exist, right? Because if we cannot define those side limit, it means that we cannot check if this left limit and right limits are equal to each other, right? That's not possible. So why should be in this case though? Because the values is still oscillating. It's the same case with the sine 1 over x. However, it looks like this is still going to number 0, right? So using a graph, we cannot figure it out. It is not possible to figure it out. We can actually guess that it is going to the 0, but we're not sure about it, right? What if it is keep oscillating near 0, so it doesn't have any value, right? What if it keep oscillating so that we cannot compare the right limit and left limit, like how I explained it with the sine 1 over x, right? So the graphing is not a good tool to evaluate this limit like right now. But let's kind of do DSP then. Let's kind of try DSP because that's like the first step that we did. But DSP, the 0 is not in the domain of the 1 over x, right? Because 1 over x, if you plug in 0, the 1 over x will going to be undefined, right? So therefore, no DSP because the domain is nothing. So if the DSP doesn't work, we can definitely use an algebra to simplify out so that the 0 can go inside the domain. However, there's no way to simplify 1 over x. This is already prime expression, which means that it cannot be simplified, right? So for this case, we can't use a algebra, right? We can use an algebra. So algebra is cut. Right? Then we can definitely use a table to see where is it going. However, even though the 1 over x is becoming the infinity, it means nothing. Why? Because sine is a periodic function, right? Sine is periodic function. So if it's a keep increasing, you know that it will be keep oscillating from 1 and a -1. The oscillating function means that the same function will be continue forever. And then you know the sine theta or sine x is always oscillating from 1 and a negative 1. So if the number is keep increasing, your value, because I told you that infinity is increasing number, right? It is not a number, but the infinity tells you that the value is keep increasing. So which means that if the values keep increasing, the sine x will keeps its oscillations between negative 1 and 1, right? So the making table does not make any sense. And even though we make a table, it doesn't help us, right? So no table. So table is not possible. Then the only way that we can do is a graphing. No, the only way that we can actually do this is nothing. There's no way to solve this problem, right? The graph doesn't help us. DSP doesn't help us. Algebra table, none of them are helpful to us. Then what should we do to evaluate this limit, right? For these cases, this is the case where we need to use our squeeze theorem. If we actually use a squeeze theorem, we can actually easily solve this problem, which is we can easily evaluate this limit. Let's kind of see what the squeeze theorem is, and then let's kind of try to solve this question using a squeeze theorem, okay? I know that some students actually getting troubles with understanding squeeze theorem, but squeeze theorem is pretty simple, right? Pretty simple to understand. But I think the wording is pretty scary for people who learn the calculus for the first time. But if you actually understand what it is, this is actually not bad. So I'm pretty sure that you guys already know what inequality is, right? It actually tells you that which one is bigger and which one is smaller, right? We use the inequality to compare something, right? Which one is bigger, which one is smaller. So let's kind of look at this compound inequality right here, that x is between 3 and 7, right? Then our possible value of x has to be between 3 and 7, including the 3 and 7, right? So the possible value will be something like 3, 4, 5, 6, 7, even like 5.5 or 4.4, right? If you actually look at the number line, number 3, number 7, between them, every number in that range are possible value for x, right? But let's say I'm actually making this range of x a little shorter. So I'm adding 0.5 on the left and then the right end, and then look at this thing, right? So which means that the possible value of x is actually decreased, right? So the possible value may like at least the integer, right? When we only count the integer, it will be 4 and 5, right? Only 4 and a 5 will work there. The 4, 5, and 6, right? Only 4, 5, and 6 will going to work. Which means that if you actually look at the number line, 3.5, let me kind of draw the same number line to make my explanation better. 3.5, 6.5, the middle value right here, right? Let's kind of look at the other one, right? 4 to the 6, which means that 4, 5, 6 are definitely works for this third inequality. However, you can definitely see that the range are squeezed, right? Then the second one. Range are squeezed. And then if you actually look at the fourth one, it is more squeezed. So between x, you can actually put 5 and 5.5, or like maybe like 4.7 and stuff, right? You can actually put a lot of numbers between 4.5 and 5.5. But what you know for sure is that your range is getting smaller. Your range is getting shorter every time when you're restricting your domain here, right? So here, look at this. So this is 4.5 and 5.5. As you see here, your range is squeezing. What if our x is between 5 and 5? Then the possible value of x is only the one thing, 5. Which means that 5, right? So as you see that, as you see that, as the number in the left number, as the number in the left and right are going to the same, approaching to the same value, right? Because as you see that number 3 was approaching to 5, and then the 7 was also approaching to 5, right? So as this both approaches to the 5, you see that the possible value, possible range of x is getting smaller, 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 right? As those both values are approaching to the 5, your range for the x value is getting smaller, 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 smaller. And when they're equals to, right? When they're equals to 5, your middle values are defined with 5, right? Because it's so squeezed that only one number can be fit between them, right? It is so squeezed. That's why we call it as a squeeze theorem, right? So let's kind of apply it with the function. So let's say gx is always between fx and hx, right? And then in with this cases, right? With this cases, let's say we're actually fx and hx are approaching to the same value, right? As x is approaching to something. So for example, let's say limit x is going to the 1, the x is approaching to the 1, the limit of fx is approaching to 2, and then let's say as x is approaching to the 1, the limit of the hx is going to 2. So which means that if I rewrite this with the inequality, limit of x is equals to 1, fx is equals to 2, and then let's say limit of x is approaching to 1, the limit of hx is equals to 2. Let's say this kind of cases are happening, right? Let's say this kind of cases are something that we want to try to get. And then if I ask you, hey, what will be the limit of gx when x is approaching to the 1? What will the value that be? But if you actually look at our previous examples, right? If the left and right numbers are 5 and 5, the x must be equals to 5. For these cases, that's exactly what's happening here, right? Because our left and right values are 2 and 2, this value must be 2 when the x is approaching to 1. Okay? So which means that these values are easily becoming 2 using a squeeze theorem. Okay? So this is actually proper definitions of squeeze theorem. So let's say the gx is always between a fx and hx, right? When the gx is between fx and hx, when x is near a, right? Near a. So it doesn't matter. It doesn't matter if this one happens in the other side, but our goal, which is when x is near a, right? Let's say the gx is sandwiched by fx and hx, right? Then if the limit when x is going to the a, the limit of fx and hx are equals each other, then gx is sandwiched, therefore it should have a same limit value as this one. Okay? So that's what the squeeze theorem is. Sometimes we call this one as a sandwich theorem. And then sometimes we call a pinch theorem because it looks like we're pinching. Let's kind of talk about the graphical way of interpreting this one. Okay. So let's say I'm actually graphing, and then let's say I'm going to draw some function, and I want to find the limit value of this, which is this is hgx. So I want to find the value of limit x is going to the a, the limit of gx, right? Let's say I want to find this limit, okay? Then what we're going to do is that we're going to find a two function that is sandwiching this value near A, right? Something near A, something like that. Let's say we are finding the value so that it is sandwiching that value at x equals A. And then let's say this value has to be hx and this has to be the fx, right? If this is the case, right? And then if we know that the limit of hx when x is going to the A is equals to L, and let's say the limit x is approaching to the A, the limit of fx is equals to L, right? Which means that these two functions are approaching to L as x is approaching to the A. So let's say this is like L, right? Let's say this is like a L, then this must be equals to L. Why? Because gx is sandwiched between hx and fx near A, right? And then because it is so sandwiched that hx and fx is going to the same limit, then it will be so squeezed, then the middle function will also get a same value as the hx and fx. Does that make sense for you? So this is a sandwich theorem. So this is a squeeze theorem. So the most important part of the squeeze theorem is finding these upper bound function and lower bound function, and then knowing their limit are very, very important. So let's kind of do some practice question, and let's kind of try this problem again, right? So in order to solve this problem using a squeeze theorem, what we need to know is that we actually need to know the bound, which is we need to know the bound function, which is upper bound function and lower bound function. And I think in squeeze theorem problem, when you see the function like sine 1 over x, those kind of, if you see those kind of function, you need to always start with their amplitude, right? That's because that's the easiest way to start the inequality, because you need an inequality, right? And you need a two inequality. So you need to actually figure it out. What should we do so that we can actually get that two inequality? That's the very important part of the squeeze theorem. But if you actually have some trig function, then those two inequality actually comes out very easily with the amplitude, right? Why? Because sine 1 over x is always between -1 and 1, right? Your sine 1 over x is always between -1 and 1. So you already get the two inequality, right? And then the next part is that you need to make sure that make sure that in the middle, your function has to be x sine 1 over x, not just sine 1 over x, right? So in order to make it to the x sine 1 over x, what we're going to do is that we're going to multiply x on every side, which means that you're going to get an inequality of x sine 1 over x and x, right? And next thing, to use a squeeze theorem, what we're going to do is that we're going to put the limit, right? Because this is what we want to evaluate, right? So limit x is going to the 0 of -x has to be less than x sine 1 over x. And then what? Limit x is going to the 0 of x, right? For these cases, and this is what we want to get. This is what we want to get, right? This middle thing. So therefore, you evaluate this thing, because your upper bound function, left bound function, the limit evaluation is very easy for this case, right? So you know that this one will be equals to 0, which is limit x is going to the 0 of x sine 1 over x. And then this one will be also 0 as well. So if you actually see that the limit of x sine 1 over x when x is approaching to 0 is sandwiched by this 2, 0. So your range is very squeezed, so that this one must be equals to 0, right? So therefore, the limit x is going to the 0, x sine 1 over x must be equals to 0 for this case. x, right? So we can actually prove that our guess, right? If you actually look at the thing, we actually made a little guess, unproved guess, that this limit is going toward to the zero, but we didn't have any mathematical proof. But here's the mathematical proof, right? By the squeeze theorem. Squeeze theorem, right? So as you see, the x sine 1 over x is always less than x or always bigger than or equals to negative x. For example, right here, right? If you draw the line, this graph is always inside this two line, which is a 1 will be y is equals to x, 1 will be y is equals to negative x, right? So this actually works like this. Let's kind of go to the next question. If fx is sandwiched by these two functions, evaluate limit x is going to the 1, fx, right? Which means that same thing, right? We can actually take a limit on all the sides. So let's kind of do that to use to use a squeeze theorem. So limit x is going to the 1 of radical x squared plus 3 is less than limit is going to the 1 of fx less than limit x is going to the 1 of x squared plus 2x plus. Yay! And then we're going to evaluate those left end and the right end with the limit using a DSP, right? Because the 1 is included to their domain. So you know that this will be 2. Limit x is going to 1 of fx. It should be less than or equals to 2, right? So this value are sandwiched by 2 and a 2. Therefore, you know that this limit of fx when x is approaching to the 1 has to be equals to 2 by squeeze theorem. Right? Very straightforward, right? Let's kind of go to this question. This question is pretty complicated, but the one way that you can actually solve this question very easily is you need to know the bound, right? I told you the hardest part of doing a squeeze theorem is finding that upper and lower function bound, right? Lower function to inequality. That's very important. So let's kind of start with this one, right? Always start with the trig, okay? Because trig actually give you very easy two inequality using their amplitude, right? Let's kind of start with this one. So you know that cosine 3 over x is always between -1 and 1, which means that 1. Let me kind of move it to, let's kind of move it to right here, which means that if you actually put it to e, because we want to make sure that the middle function are similar to these, our objective function, right? So we're going to put e on everything. So e to the -1 and e to the cosine 3 over x and e right here, right? And then the next step that we're going to do is that we're going to multiply x because our objective function has an x. Therefore, we're going to multiply x on every side. And you're going to get x e to the -1, x e cosine 3 over x, and less than x to the e, right? And then what we're going to do is that we want to evaluate the limit. So therefore, we're going to put our limit on everything. So limit x is going to the 0 of x to the e to the -1 is less than limit x to the going to the 0 of x e to the cosine 3 to the x. And oh my god, I'm running out the space. And then this should be less than or equals to limit x is going to the 0 of x to the e, right? And then because as x is approaching to the 0, you know that this limit value is going to the 0, right? Because of the x, right? So therefore, you know that 0 limit x is going to the 0 of x e to the cosine 3 to the x is actually going to the 0, which means that you can easily see that the limit value is sandwiched by this 2, 0 on the right and the left side. Therefore, this one must be equals to 0, right? By squeeze theorem. Okay, let's kind of do the next lesson, next question, which is you get this one. This question is a little bit difficult, so let's kind of focus on here. So let's say the limit of fx as x is approaching to the -2 is equals to -2. And then let's say the limit of gx as x is approaching to the -2 is 2. And then we need to evaluate this one, right? We need to evaluate this one. But it should satisfy these three conditions, right? When the fx is odd function, the gx is even function, and the hx is between fx and gx, right? Because the question already gave you this inequality, right? Because it already gave you this inequality, it actually gives you the very strong signal that we need to use a squeeze theorem. Right? It actually gives you a very strong signal that we actually need to use a squeeze theorem to do this, right? Then this is our issue because we want to actually evaluate the limit value of the hx, right? When x is approaching to the 2. So that's why we need to put the limit on everything, right? On number 3. So what we are going to get from number 3 is we are going to get limit x is going to the 2 of fx less than limit x is going to the 2 hx less than limit of gx as x is approaching to 2. Very good. So if we actually can figure it out, this value and this value, we can actually get our value in the middle using a squeeze theorem if these two values are equal to each other, right? But let's kind of look at our another conditions right here. Let's look at this, that we don't have that. We don't have this limit value because every x is going to the -2, while we need the limit of fx and gx when x is approaching to the 2. But if you look at our given limit, the x is going to the -2. Then what should we do? Let's kind of try to use these conditions in 1 and 2. Then fx is odd function, right? This is something that you need to review, right? If it's an odd function, it's reflected by origin, right? Which means that it's like a cubic function, right? So let's say this value is like -2, -2. Then the other side, you're going to have a 2, 2. That's what it means by odd function, right? If you have a -2, -2, then you will definitely have a 2, 2, right? So which means that the fx is odd function. Since the fx is odd function, if limit of fx, x is going to the -2 is equals to -2, then you know that what? Limit limit of fx as x is approaching to 2 has to be equals to 2, right? And then the same thing, the even function, right? Even function means the what? It is always reflected by y-axis. So it means that if you have a -2, 2, then you should have what? You should have 2, 2, right? That's what it means by even function. You're reflected by a y-axis. So it means that using these conditions that gx is even function, if limit of x is approaching to -2, the limit of gx is equals to 2, then we also know that limit of gx when x is approaching to 2 is also equals to 2, which means that these two values are the same, right? So you know that this has to be equals to 2, this has to be equals to 2. So therefore, you can conclude that limit of hx when x is approaching to 2 has to be equals to 2 by a squeeze theorem, right? So I put this problem here because you actually need to know what the even function and odd function is and how they behave in graph. And the odd function means that they are reflected by origin. Even function means that they are reflected by y-axis. So make sure that you know that. And then we can actually definitely try to use these conditions to find the limit and squeeze theorem. We can actually get the answers. Okay. So summary, the summary is the squeeze theorem is a very useful tool for evaluating the limit of oscillating function that has a clear upper and lower bound function. Okay? And when you're using a squeeze theorem, finding the upper and lower bound function is a key to success. So this is definitely the hardest part of the squeeze theorem if you actually get it on the test. Okay? Finding the upper and lower bound function is the hardest part of the squeeze theorem. So professor can be very evil, but not the AP though. AP actually give you very clearly what your upper and lower bound function is. So it's pretty easy to find for the AP, but not for the university exam. So make sure that when you're doing practice for squeeze theorem, you focus on finding the upper and lower bound function. Okay, that's very, very important. Okay, so next video that I will go to make is that it will be about continuity. Okay, this is very important, and AP loves continuity as well as your professor. So make sure that you take the next lesson to get full understanding of what the continuity is. So great job. I will going to see you on the next video. Bye.